Welcome to GCSE topic 11 called Organic Chemistry. This topic builds on the content from topic 5, which was crude oil, and in order to support you with your learning in this topic, we've produced a series of videos, some notes which will be available on OneNote, some quizzes and some past paper questions. So let's move on to the first topic. So in this topic we're going to look at an introduction to organic chemistry, sort of start it off, and in this topic we'll look at what organic chemistry is, we'll look at how we classify organic compounds, and we'll look at how we represent organic compounds.
So, what is organic chemistry? Well, quite simply, it is the study of compounds which contain carbon joined to hydrogen. And there are many millions of molecules possible which contain carbon and hydrogen. And so, therefore, the study of organic chemistry is huge as part of chemistry. Now, why are there so many compounds possible containing carbon-hydrogen bonds? Well, the first reason is that carbon atoms are able to form 4 covalent bonds and so can join to other carbon atoms to make great big long chains, and they can also join together into rings as well. And a couple of examples there to show you the atoms joined together in a chain, maybe with a branch in it, or the atoms joined together in rings. Now, the other thing that carbon can do, of course, is can bond covalently to other atoms as well as carbon and hydrogen. So you can have oxygen, you can have sulfur, you can have halogens also joined in to make organic compounds. Most organic compounds originate from crude oil, which is made from the remains of decomposed living organisms, etc. And so that's why it's called organic.
Okay, we're now going to look at how we classify organic compounds. So organic compounds can be classified according to something called a functional group. Now, a functional group is an atom or group of atoms which determine the chemistry of the compound. And so in this example here, we have a molecule with 2 carbon atoms and 6 hydrogen atoms, and this is a hydrocarbon, a molecule which contains carbon and hydrogen only, and specifically it is a saturated hydrocarbon because all of the bonds between the carbon atoms are single covalent bonds. So this is a saturated hydrocarbon. So the functional group here is a saturated hydrocarbon. The next way that we classify organic compounds is by something called a homologous series. Now, a homologous series is a family of compounds which all contain the same functional group. And because they contain the same functional group, they have very similar chemical properties. There is a trend in their physical properties. So as the molecules get bigger, their melting points get higher because they have stronger intermolecular forces between the molecules. Each member of a homologous series differs from its neighbour by only 1 carbon and 2 hydrogens, and all members of a homologous series have the same general formula, and we'll look at what we mean by a general formula in the next slide. But here we have an example of a homologous series. This homologous series is the alkane series, and we've got 4 members of the alkane series here. Each of them are hydrocarbons. They're saturated hydrocarbons, but as the members get larger, we add more carbons, more hydrogens, and the molecules are then different. So that's how we classify organic compounds. We're now going to look at how we represent organic compounds, and we'll use as our example for this one ethane. And there are several different ways that we can show organic compounds. So the first one is the molecular formula. A molecular formula shows the actual number of atoms of each element within a molecule of a compound. So the molecular formula for ethane is C2H6, which means every single molecule of ethane contains 2 carbons and 6 hydrogen atoms. The second way that we can represent organic compounds is with an empirical formula. Now, an empirical formula shows the simplest ratio of atoms of each element within a compound. So the molecular formula for ethane is C2H6. That can be simplified to CH3. We can divide 2 and 6 by 2 to get a ratio of 1 to 3. So the empirical formula for ethane is CH3. You can calculate an empirical formula based on information about the mass of each element within a compound. And sometimes you might be asked to use information to calculate an empirical formula. You might be provided with the MR, the molecular mass value, in order to calculate a value for the molecular formula for a compound. That sits mostly within topic 8, the calculations topic. So the empirical formula for ethane is CH3. I mentioned on the previous slide the idea of a general formula. The general formula for a compound is where we use an algebraic representation. So the general formula, instead of putting a number for the number of carbon atoms, we use the letter N to represent the number of carbon atoms. And for an alkane, which is what ethane is, the general formula is CnH2n plus 2. So ethane contains 2 carbon atoms, therefore N is 2. 2 times 2 is 4 plus 2 is 6, therefore there will be 6 hydrogens. And so that's how, if we know that there are 2 carbon atoms, we can calculate the molecular formula from that general formula by substituting 2 in for where it says N. Now we get on to the more useful representations, the representations that will come across much more frequently in questions. So a structural formula shows each of the carbon atoms separately with as many hydrogens or other elements there are attached. So for ethane, there are 2 carbon atoms. Each carbon atom contains 3 hydrogen atoms attached. So the structural formula is CH3CH3. This is more useful than a molecular formula because it gives us information about how the atoms are arranged, how they are attached to each other. And then finally, there is the displayed formula. This is a type of structural formula where every single bond is represented by a line, and this really helps us to visualize how the atoms are joined together. So again, in ethane, the displayed formula looks like this. Each carbon has 4 covalent bonds, and we generally draw those bonds at right angles to each other, with 3 hydrogen atoms attached to the first carbon, then a bond joining the 2 carbons, and then 3 hydrogens attached to the second carbon as well. You will find that you'll draw a displayed formula probably more frequently in organic chemistry questions than any other way of representing an organic compound. Okay, so we've looked here very briefly at what organic chemistry is. We've looked at how we classify organic compounds by their functional groups and into homologous series. and we've looked at the different ways that we can represent organic compounds. So what I'd like you to do now is to have a look at a brief exercise. So butane is a member of the alkane homologous series. That means that it has the general formula CnH2n plus 2. Butane contains 4 carbon atoms. What I'd like you to do in a minute is just to pause the video and to write down the molecular formula, the empirical formula, a structural formula, and then a displayed formula for butane. So go ahead and pause the video, complete that, and then come back to have a look at the answer. I'm going to carry on now in 3, 2, 1. Here are the answers. So the molecular formula for butane is C4H10. So using the general formula CnH2n plus 2, if n is 4, then 4 times 2 is 8, plus 2 makes 10. So the formula is C4H10. The empirical formula, we can halve our numbers, we can divide through by 2 to get C2H5, which is the simplest whole number formula for C4H10. So C2H5 is the empirical formula for butane. The structural formula has 4 carbon atoms. The first carbon atom has 3 hydrogens. The second carbon has 2 hydrogens, the third carbon has 2 hydrogens, and then the last carbon has 3 hydrogens again. And then the displayed formula, similar to the structural formula, but shows all of the bonds using hydrogen atoms. So I hope you got all of those right. The next thing to do is to look at a quiz, just covering some of what we've talked about in this session, and then the next topic after this looks at how we go about naming organic compounds.